Okay, our next speaker is going to be Rob Tipshirani from Stanford University. Rob is a professor in the Department of Statistics and Public Health Research. He's won the Cox President's Award, and he's a fellow of the American Statistical Association, the National Academy of Sciences, and the Institute for Mathematical Statistics. His research interests include applied statistics, data mining, biostatistics, in particular genomics and proteomics, and he's very well known for his work on the Lasso and analysis of microarray data.
Thank you very much. It's a real pleasure and honor to be here on this historic occasion, and I'm very happy that statistics seems to be growing, thriving at MIT, and I look forward to an exciting future. I guess I have the last word. Well, at least I'm sure that's not going to be the case. So I'm going to talk. I thought about to talk about. So I'm actually going to spend some time on an applied example, rather than make general comments. But in the context of the example, I'll make some general comments. And the second part, which is related to the first, is actually a new theory of post-selection inference, which applies to the Lasso and a lot of other adaptive procedures. So it starts from the applied and moves to the theoretical with links in between. So broad outline, the example, the collaboration, ongoing collaboration in cancer surgery, sparsity in the Lasso, which I seem to spend most of my time working on that now, and then new tools for selective inference. So, but a little bit of philosophy. I was a student of Brad Efron's back in the 80s, and Brad said to me, well, maybe about 10 years ago, he said it's hard for him to believe that in the old days he used to sit in his desk and think about what to work on, right? And maybe in the 60s and 70s he would, read papers and just think, gee, maybe I should work on this problem. And of course he evolved, as most of us have, to a situation where that's not the paradigm, right? So this is the old paradigm is I guess is mostly before my time, where you'd sort of sit there and think about things to work on as a theoretician. You'd work on them, you'd write papers, and then there's an arrow. This arrow is kind of jagged because this is a long time. Eventually the theory might make its way into actual tools that statisticians make, and then eventually maybe even longer into practice, right? So this paradigm was kind of like this, not very efficient and sort of in only one direction. But the new paradigm, I think, is more like this, right? Where all three inform the other ones, right? Where people work on theories that very quickly, because of things like the web and R and other things, are turned into tools for statisticians and are put into practice much more quickly. And then there's feedback in every direction. And I think MIT, for example, is very well positioned to invoke this paradigm because you have so many good applied scientists in the same place, right? That with stats here, I think it'll be a strong wheel in this hub, right? And there'll be communication in every direction. And Stanford's like this now. It's taken a long time to evolve to that situation. I think it's a very it's a very efficient way of doing things. It's also a lot of fun, right? Because you get to talk to people in different sciences. And there's very smart people in other sciences, who know a lot of quantitative things. They're not formal statisticians, but you learn a lot from them. I learn a lot from them, right? Just understanding how they think, how they view problems, suggests to me new ways of approaching my problems. And it changes the way I think. And I'll give an example of that now in the cancer collaboration. But I wanted to just say sort of my gem of wisdom. I think this slide came from an early version of this talk I gave at CMU last fall in machine learning. That really important to talk to real scientists, to work with real scientists. It's not the same as working with real data, right? Actually, working with real scientists is important because it keeps you grounded. You sort of if you sit at your desk and sort of figure out new ways of doing things, then you fool yourself and think, gee, I've solved this really. You don't realize the assumptions you're making are unrealistic, or the data that's required is not. You can't actually collect that kind of data. When you talk to real scientists, it keeps you grounded as to what's important, what's feasible. It also makes you communicate your approach to the scientists in a non-technical way, right? You don't get fooled by your own sort of models and equations. You've actually got to explain to them in simple terms what you're doing. And when you do that, you often look back and say, well, actually, that assumption you're making over there, that's not reasonable in my system. I don't think that's true. So this sort of two-way communication really helps both sides. Data doesn't talk, but scientists get confused, ask you questions. So I think it's really, really important for people in statistics to really to work with real scientists, because it helps, hopefully the scientists, but also helps you in ways which are unexpected. And then I also want to make the point that when you do collaboration in statistics consulting, most of the time the advice you give is very simple. The answer is go collect some more data, or or your design was flawed. Here's what you should do, right? Or here's a t-test, or here's a box plot. That's okay. I mean, at first I thought, I've got this PhD in statistics. What am I doing telling me to use a box plot? If that's what's needed, it's great. And common sense, or quantitative common sense, isn't that common, right? So it isn't. So I think, whatever is needed, most of the time what's needed is a simple piece of advice, right? Sometimes it's a happy situation where, you got to apply the lasso or whatever your favorite method is, but don't sort of try to force a square peg into a round hole. So that's my only sort of general philosophy. Let me talk about this a detection problem in cancer, which I've been working on now for a number of years, a few years with people in chemistry at Stanford, which has been a lot of fun. It's for stomach cancer, which is a very bad disease. Somebody gets stomach cancer, the surgeon goes in and wants to remove just as much of the stomach that's cancerous and leave as much functional stomach in. So the person can have a reasonable quality of life. So Dick Zare, who I've known a number of years, a famous chemist, and his postdoc came to see me, and they said, could you help with this problem? Here's his postdoc, Livia. Here's Richard Zare, chemist, and George is a oncologist, cancer oncologist. So here's sort of in cartoon form what the problem is. We have the stomach is going to be, which I've labeled in red cancer and two kinds of normal tissue. The surgeon wants to go in and remove the piece that's cancerous and wants to just remove just enough to leave as much healthy tissue in as possible. So what happens now is, while the patient's still in surgery, this piece is removed. A pathologist looks at the edge or the margin and sees whether it's clear. If the edge is clear, he go in and tell the surgeon, well, you're done, you've got it all, you can go close up. If there's cancer along the margin, then he tells the surgeon, actually, you're not done, you have to go back and get some more, right? So, and this again, while the patient's still in surgery. So this is an important thing to do, obviously, and to do in real time and do it in an accurate fashion. The problem is the error rate, depending on who you ask, can be as high as 20% in difficult cases, right? It's very hard, it has to be done in real time, it's a frozen section, so the topology of the cells gets changed by the freezing. It's a challenging thing in some cases, in a lot of cases. So they wanted to do some kind of machine learning approach to help the pathologist. So mass spec to the rescue. This is a new kind of mass spec, which I don't really understand the details of. If anybody here asks questions, I'll say that now. But it's a kind of mass spec where you can get a spectrum per pixel in the tissue. So a charged spray is fired at the sample, and then surface ions are released from the sample, and they go into a mass spec. But what you can get in, I think, about a minute is a mass spec of every pixel in an image. Okay? And this, so this is,
excuse me,
yes.
Biopsy?
Biopsy. This is during surgery. So during surgery, yes.
During surgery.
Yes. So this is, roughly speaking, the kind of data we have. For each patient, we have the two kinds of normal tissue and some cancer tissue, each of these little pixels, these squares. Each square, we have a spectrum, okay, at about 11,000 sites. Okay? So our feature vector is going to be the spectrum. We have at every pixel. Okay? And we want to classify, basically, each pixel as being either normal or cancer, based on the spectrum. And we'll take a grid of about 11,000 values over this continuous spectrum, and those are our features. Okay? And we have that at every pixel. And we're going to ignore the fact, for now, that the pixels are nearby each other. We're just going to treat them as a set of observations. Okay? Turns out that doesn't really seem to help very much, treating them as adjacent pixels. So our initial training samples, 20 patients, each with data like this. Okay? Two kinds of normal and cancer, and a spectrum. Okay? And we have the true labels, though. So actually, the data here, the labels were gotten not in real time, but after a few weeks of further testing in the lab by the pathologist. So the kind of test that you can't do immediately, they have a sort of a gold standard test, which they believe after 2 weeks is probably the right label. Okay? So it's basically a classification problem. So here's our data looks like now. We have for each patient, each row is a pixel. We have our features going across here, and we have the intensity value in the spectrum of each of these cells. And then we have our true label, our pretty much true label for the sample. And we want to basically classify the pixels based on the spectrum. Okay. So this is kind of what the data looks like for one patient. This is these are pieces, and the spectrum is sliced in various intensity levels just so you can see it. And then here's the actual staining, which the pathologist does, which indicates that this is, here we have cancer, epithelial, and normal stroma. Okay.
I'm sorry,
Yes.
There's a little bit of normal tissue that's coming out. They're getting the tissue that's taken out of it, right?
Yes.
So there's a little bit of extra normal tissue that comes out of the
Well,
stuff
I should say,
tissue,
so
right?
the training sample, so this training sample is not actually from the cancer surgery, but it's from, well, it's from the surgery, but it's also augmented with some normal tissue. So we actually have a non-trivial amount of normal tissue for each patient. Yeah.
What happens in is, so you resect the what you think is the pathology, and there's a margin,
Yeah.
and you label it. And that's what you send to pathology.
And it's got some of each.
It could, and you've guessed just based on your feel where you think it is,
Yeah.
and now you want the pathologist to tell you, yes, that margin is clear, there's no cancer, or unfortunately that margin has cancer, you have to go back and take some more of the stomach.
Okay.
Thank you, Emery. So we need a classifier, basically, a pixel-based classifier that can deal with about 11,000 features, most of which we don't think are important. So we like two things. We like to be able to classify in an accurate fashion, but also pare down the number of features to a small number so that the biologist and the chemist can look and say, I see, these are the important parts of the spectrum, and maybe use that to understand the biology behind the cancer, right? And maybe hopefully be able to treat it eventually. So we like a sparse model both for good classification, but also for interpretation of the signal. So we use the Lasso, and I just review the Lasso in the normal linear model case first, which you've seen probably before, also seen today in Peter's talk. So a regression situation where I've got n observations, p variables. I've got coefficients beta. Least squares, of course, just minimizes sum of squares of error, and the Lasso uses an L1 penalty, right? And we'll pick this bound or do the equivalent Lagrange form in which, and that's the smaller the bound, the more sparse the model. So this is the sparsity Peter was talking about, and this picture was in the original Lasso papers showing that the effect of the L1 penalty, that if you do least squares, your contours of the objective function are ellipses. If you use an L2 penalty, which is ridge regression, right, the solution you get, the first place the contours hit the constraint region is not likely to be at a place where one or the other is zero, because the constraint region is smooth. The Lasso uses an absolute value penalty. If you hit a corner or an edge in higher dimensions, you get sparsity, right? So just the change from L2 to L1 gives you sparsity through the geometry of the constraint region. And it's a convex problem, so we can solve it efficiently. And in our data mining book, we have this example in prostate cancer, just to show you the form of the solutions tends to be, as you vary the bound from small to big, the solution goes from very sparse to the full least square solution. Right? And normally the bound is chosen by something like cross-validation, right, which tries to trade off the fit with the sparsity of the solution. So back to our situation, we're going to use a form of this, but of course the loss function is not going to be the least squares because the response is a class label, 3 labels, right? So the multinomial model is appropriate. So the log odds of each of the classes will be modeled as a linear function. Now these are the features. These are the spectrum value, the height of the spectrum at position J. So there's about 11,000 of these in the sum end. Okay? And again, we'll have a bound on the coefficients, should be beta JK there, which will vary the model from very dense, which means use all the peaks, to very sparse. Okay? And again, so fast computation is essential. This has been doing work for many years with my friend and collaborator Trevor Hasty, who's a classmate of mine at Stanford, and Jerry, who's one of my teachers and now one of my colleagues. GLMNet's a program we've written. Jerry wrote the Corvette in Fortran, which I know is, nowadays, you say Fortran, people sort of snicker like, you got to be kidding. But it's actually Jerry's a master programmer at Fortran. He's been doing it for many, many years. And he worries about every little detail. And having done that, the algorithm is actually very fast. I mean, I'm not saying it's the fastest around. There's a lot of people in numerical analysis, computer science, who've written L1 algorithms. But it's certainly in the mix of some of the fastest algorithms. And it's in R. I mean, it's an R interface. It's also in MATLAB if you want to use it. When I put Fortran there, I found this quote about Fortran, which is pretty kind of funny. My daughter is a computer science graduate. When I mentioned Fortran, she also snickers, like, I can't believe that you guys are actually using Fortran. But I challenged her to write a faster algorithm. Maybe she might well be able to do that, but okay. So how does this work? So now we take the training data, we just run the lasso, we apply cross-validation to choose the bound, and the error rates or the percent correct is in the range of 94 to 98%, right? Which is very promising. Cross-validation and then a separate test set, a little worse, but still quite promising. And our collaborators are very excited about this. I'm actually trying to hold them back. So we haven't tested it on hard enough cases yet, which we're actually doing just now. It's working not as well, but it's still quite promising. And they like it also because the number of peaks is about 129 peaks. So it pares down the 11,000 to 129. And they've looked at them, and they're, of course, they can always tell a story, right? You know, people work with biologists. Whatever you give them a gene list, proteins, they have a wonderful story to tell. And I mean, their story might be right, but among the 129, there's apparently things that are very interesting to them, at least in the biologically. Other question, Peter?
Yeah. Is proximity in terms of the label and the variable correspond to proximity in the tissue? In other words, if
label and the variable is in the spectrum. So, right, the variables are along the spectrum here.
okay.
Whoops, right? It's nothing to do with the tissue. So I have this in every pixel. I'm not actually using proximity in the pixels at all. My attempts to use that haven't really helped. And if you overuse that, if you smooth too much, you're going to sort of smooth away the thing you're looking at. So it's so far just treating the pixels as separate, as independent, seems to be the most effective. So yes.
So did you try to actually just fit a linear model and see how, like, rather than doing multinomial, just
A linear model? I don't think so. Well, of course, you got 3 classes here, so how are you going to do that? They're not ordered. Maybe with 2 classes you could do that, and you probably wouldn't get anything that different. One advantage of this is you get probabilities which are between 0 and 1, which I've indicated here, by the way. So here's the sort of the true pixels. The identity of the true pixels they've been arranged in true categories, and then here's the 3 predicted probabilities. We hope to see is sort of the green is higher in all the green regions and red, and it's quite good. I mean, there are places where it's wrong, but it's not. So not only is it right, but it's pretty sure it's right. These are cross-validated. Okay. And these are sort of these are the weights you get out. You get 1 per class, right? 1 per class per site, saying, you know, high peak in this class, high peak here means that you have more chance of cancer, or a high peak over here means you have more chance of being normal, etc. And this is just an example in one patient of here's the stain, here's the true class, and here's the prediction. And it's not perfect, but it's quite good. Was there a question? Yes.
So you think that the features of neighboring pixels would be highly correlated, or is that not the case?
The pixels are being treated independently here.
Right, so I guess I'm trying to get some intuition as to why using neighborhood information would not help. Is it because the features of neighboring pixels do not look like each other at all?
Well, the features might look like each other, but
Surely an
yeah.
interior, if you take an interior
Yeah.
point to a region,
Yeah.
you know what it is.
But the interior points are pretty easy. The question is sort of near the edge between classes, can you do better by borrowing information? And you can go either way, right? You can borrow information, but you can over-borrow and you can over-smooth. Yeah. So it's tricky. And I did try other approaches to support vector machines and deep learning, and neither really helped. Support vector machines are a little bit worse, weren't as easy to interpret. Deep learning, which actually I don't know how to run yet, so I'm a friend of Jeff Hinton's. When I used to be at Toronto, I had one of Jeff's students try it, and it didn't. He said there wasn't enough data, basically. The data was not big enough for deep learning. So he wasn't able to do any better. Actually, maybe even do as well as this, and the model is much more complicated. But you know, it's not all things are rosy. So here's an example of sort of the feedback between an application and now theory and statistician. So you know, I ran this, and the collaborators were very happy, and then my collaborator now we're starting to run on real surgical samples. So she came to me, and she goes to the operating room and brings back samples. She said, okay, you've got the classifier, it's really great, can you classify this one for me? And I classified it, and it said all cancer. Very heavily, most of the pixels were cancer. And then she came back a week later and said, well, the pathologist says you're wrong, like this is normal, right? So it was completely wrong. So then we looked at what happened, and one thing of is the new sample point was not in the convex hull of my training data. Right? We're 11,000 dimensional space. Here's my data, and the point turned out was like far away. And why was that? It turned out the fat content of the tissue was much greater than the training sample. Maybe the tissue was from a maybe it wasn't from the stomach, maybe it was from nearby the stomach. Composition-wise, it was very different than my sample. And that was why it didn't work well. But this brought up to me a sort of a general problem is, how do you, first of all, you hope in that situation that if the sample is sort of weird looking, that the classifier will just say, well, it'll throw its hands up and say, well, maybe it's a third, a third, a third, right? But unfortunately, it's not going to happen, because think about it, like, here's this with two features, here's two classes, here's the query point, right, that's outside the convex hull of the data. Remember, multinomial probabilities are relative probabilities. So if I compute the relative probability of this point under these two classes, it's much higher under the green class, because it's relatively closer to the green class. It's far from either one, but the relative probability is what happens. So it's not the case the probability will come out and say, it's 50-50. It's probably going to say, it's 0.8 maybe being green class, and that's not helpful. So now, yes?
Rob, would actually this be a case where robust regression might help? In other words, log LA,
Maybe, well, so.
With the Lasso.
Well, the answer is I don't know. I actually have a student working on this general problem is how do you do this kind of classification in high dimensions is the problem, right? This picture is fine, but now we're in 11,000 dimensions. You might say, well, just if the point's far away. Well, what does far away mean, right? Every point's far away in 11,000 dimensions, right? And what subspace has got to be far away? So, and which directions are far away? So I think it's a difficult problem. It hasn't really been, as far as I can tell, hasn't been treated by statisticians or even machine learning people. How do you detect when a point is far away? So that the classifier can once in a while say, I have no idea. I'm not willing to make a bet here. And that's obviously important in this application, right? If this goes into the clinic, we don't want to always be making predictions, some of which are completely unfounded, right? So that to me was a really interesting problem that seems basic, but I never thought about it in 11,000 dimensional space. And I think the answer, at least to us, is not easy yet. We have some ideas, but nothing that's really useful. So that was a nice example to me of a real applied problem feeding back into a research problem. So moving forward, we're doing a lot more testing, and that's happening now in other cancers as well. And then another question is, what role should the algorithm play if this is successful? Like, some people say, well, let's just put the computer in the operating room, and that's that. Well, if I was a patient, I wouldn't be very confident at that point. I'd like to have it as a second opinion for the pathologist. I'm not for one so confident in machine learning or even my own coding that I want the algorithm in there. Was there a question?
After the event?
Is the doctor
Still trusting you?
Yeah, because actually I'm seem to be more cautious than they are at this point. Like they're excited, and maybe because I'm on the inside of the statistics, I realize that there's a lot of uncertainty, both in coding and in models that we shouldn't trust this thing immediately. So this is an exciting project, and to me it's real. First of all, obviously it's nice to be doing something with a public health potential of helping people, but also it brings new problems. I mean, there's lots of other things we think of, like the fact that we want to train this classifier per patient, right? Not every patient's the same. Maybe a better way to go is to take some normal for that patient, take the existing model, sort of tweak it a bit to train for that particular person, and now make the prediction. So there's lots of ways in which this might be made better. So second half, which actually relates to the first, is also going to relate to the Lasso, but rather than prediction or classification, we're going to talk about getting p-values and confidence intervals for the Lasso in stepwise models. John Tukey talked about the different kinds of analyses, right? And makes the point, of course, that it's not fair to search for hypotheses on the same set of data and then do the test on the same data. So you search over the data, find an apparent pattern, and now use the same data to test. Well, I want to show you that we made some progress in actually doing this using the same data in what's called post-selection inference for get p-values and confidence intervals in the context of the Lasso again, and also for stepwise regression. So this is some new work that's been happening at Stanford, mainly with John Taylor, myself, and lots of our grad students, and also my son Ryan at CMU. Oh, so here's the first paper on this, which has been published. There's only one that's been published. All Canadians. Here's John, Richard Lockhart's. Oh, that's an old picture of me. And here's Ryan, Ryan's my son and a professor and a colleague of Rob's at Carnegie Mellon, who's been also involved in this work. And working with John Taylor is my brilliant youngish colleague. I think it's well described by this old cartoon, right? And the polyhedral lemma I'll tell you about right now. This is John. Oh, this is John. This is me, right? Basically, John comes up with these kinds of miracles about every week, and I'm trying to catch up and see what he's doing. And you'll see some of the theory he's come up with right now. And just one bit of self-promotion. My excuse for putting this up here is that most of this work is unpublished, but this book, which is coming out next month, has a chapter on selective inference and describes some of the work you're going to see right now. Most of the other work isn't published yet. The previous paper you saw on this slide is a large sample version, but the work you see now is actually for finite samples and gives you an exact result, an exact way to get p-values and confidence intervals, assuming just normal errors. I'll describe that. So let me first of all show you what we get, and then I'll tell you how we get it. So we'll talk about two methods, forward stepwise regression and the lasso, and they both sort of fall into this theory. So forward stepwise regression, this is an example again for the prostate data. This is in our book. There's 80 or so observations and 8 variables. We've done forward stepwise regression in the usual way, right? We add a variable in, the most correlated variable with the outcome. And here's the variables come in this order. Here are the p-values that we normally see if we run R or S+, right? They just basically, they compute a z-score and they convert to a probability. And here they are, and it's telling us there's probably maybe 4 important variables, right? But these are fiction, right? We don't believe these, right? We tell ourselves, well, gee, I've selected the variable, I've applied a greedy algorithm, but I'm going to forget about that. I'm going to compute a p-value, right? And we ignore this because that's all we really have. We don't have a way of computing a p-value which actually adjusts for the selection we've done, right? So we know these are too small, but we at least if you're like me, I use them anyway and sort of just try to apply some caution, right? Well, we can get, this column is actually p-values which adjust for the selection that's occurred in the process, right? Each of these p-values. So, for example, this p-value is the p-value for this guy, accounting for the fact that it's the second variable chosen in this sequence, right? And it's the best among the remaining 7 variables. Okay? So these are the p-values. I want to show you how we'll get these. Okay? And these are post-selection p-values. Okay? In a similar way, the lasso with fixed lambda, we can get p-values and confidence intervals for the variables. So here's an example. HIV data, there's, I don't remember exactly, maybe a few hundred variables. I applied the lasso with a certain lambda that gave me this many variables. These are both simple confidence intervals, naive ones, just using least squares theory for the variables, and then the ones that adjust for their post-selection are the beige ones, the later ones. They're much wider typically, right? As they should be, because these guys here, the dark ones, don't adjust for the fact that these are the best 7 out of however many variables, right? And the lasso, of course, is a greedy kind of algorithm. It's, for each lambda, it's picking the best coefficients. The active set is the best it can find to make the fit as good as possible under the constraint of the L1 constraint. So the selection there is, it distorts our results, and we have to sort of adjust for that. And that's what the beige ones do. Okay? So these have the property that under normal errors, for fixed lambda, the probability, the selection interval will contain the true value with the right probability, exactly, right? With normal errors in finite samples. So I think it's really exciting. And I'm going to tell you where this comes from now. Okay? So it's basically what we call the polyhedral lemma, which is due to John. We've got it now. We've got it in about 6 different papers now, but it's I don't think they're all sort of they're all impressed, or at least being under review. The textbook I mentioned has this in one of the chapters. Here's the sort of the core result. So we have data which is normal with some mean and covariance matrix. We have a selection which is polyhedral. So we've done a selection. For example, we've run forward stepwise for some number of steps, or we've applied the lasso with fixed lambda. In both those cases, we can express the selection in this form for some matrix A and some vector B. Okay? For example, forward stepwise regression, if you've chosen a certain set of variables with certain signs, that means that the inner products were in a certain order, right? Like the inner product of the first variable with y was the largest. If that's the case, then the first variable is chosen, right? So that selection, you can try to imagine, is a polyhedral. There is an A and a B that you can write down that describes that selection. Okay? For the lasso, if you fit the lasso with fixed lambda and you get an active set of certain variables, that selection can be written down as in this form. Okay? So you know A and B.
Sorry, I don't understand. What is a selection? What mathematical object is a selection?
Selection means, well, it means that in this case, y falls in this polyhedron. So the selection is a set of a restriction of y to a certain set, basically. So, for example, for stepwise regression, a selection is you choose a certain set of variables with certain signs, and that means that restricts y to be in a certain polyhedron. In other words, it's the set of y's that would give you the same set of events, the same set of variables that are put in the same order with the same signs. For the lasso, it's a set of y that would give you the same active set with the same signs. Okay? So, and there's a large set of selection procedures that you can describe in this way. Not everything, like some of them are non-polyhedral, but this is a pretty useful set. So if you have this, then it turns out that here's the theorem. It says, if you're interested in a contrast of y, for example, a regression coefficient, right? A partial regression coefficient, its distribution conditional on the selection is a truncated normal. Okay? I mean, without selection, it's normal, right? If I just do a regression with fixed set of variables, and you ask me for a regression coefficient, the PDF of a regression coefficient, it's normally distributed with certain mean and variance, right? Well, the effect of the selection is to truncate the normal, and the truncation limits you can derive from A and B. Okay? So you do a selection, I can compute the lower and upper limits, and this holds exactly in finite samples, which means I can invert the statement in order to get a confidence interval, for example, for eta transpose mu, where mu is the mean of y. Or I can get a p-value for testing whether eta transpose mu is 0. Okay, so it's a very powerful thing. There's a nice picture that sort of says what's going on. Here's my selection event. Okay, this is my polyhedron. I've run forward stepwise, for example, for a number of steps. What that implies is that y falls in this yellow region. What does that mean? If you give me a new y that falls in the same region, I'll get the same set of variables and signs if I apply forward stepwise to that y. With the features are fixed here. Okay? And what I care about is eta transpose y. So I want to know, I want to infer about the contrast in this direction. What we do is, in order to prove this, the truncated normal result, you condition on the orthogonal projection of y in the orthogonal direction of eta transpose. And that means that you get a truncated normal on this line between a lower bound and upper bound. Okay? So that's the geometry. But just to give you some intuition, where's all this coming from? It's like, here's a way to think about it. Suppose, again, a forward stepwise regression. Where does the polyhedral lemma and the truncated normal come from? Suppose I run forward stepwise regression, and I choose predictor 2 at step 1 with a positive sign. Okay? And now I want to understand the, and I want to infer about the coefficient of that variable at step 1. But somehow I have to adjust for the fact that that guy won a competition, right? He's not just any old variable. He's the best of p variables, right? Well, basically, if you think about the competition, the fact that he won means that the inner product with y, his inner product with y is bigger than all the rest, right? Because he won the competition, okay? So we want a condition on the set for which that occurs, right? And that can be written as a polyhedron, right? Because all the a's will have inner products involving the variables and y, and the b is actually 0 in that case. Well, it turns out that the lower limit is just the second largest inner product. So in other words, if you tell me that he won the competition, I know he was at least as good as the second place finisher, right? And that's actually has content, because the second place finisher with many, many variables is doing pretty well, right? So if you told me he won the competition, I know that the selection implies that he's at least as good as a second place finisher. So if I'm to be impressed by him, he better be a lot better than the second place finisher, right? That's the way to think about it. With small p, then that's not the case. Then he can just beat the second place finisher by a bit, and I'd still be impressed. So that's where the truncation comes from. It's telling us, sort of, I did a selection. That means I ran a competition. Now I want a condition on the results of that competition in order to judge the winner in the context of the competition. And that's sort of a high-level way of saying what this truncated normal.
Even if that's not very impressive, but he is still at least as good as the second finisher.
Yes.
But it's not surprisingly better than the second finisher.
Well, imagine you had the global null. All the coefficients were 0, right? And somebody has to win, and he's going to win with a z-score that's pretty good.
So
but Yeah, I mean, I'm just sort of describing in English what, this is just a mathematical result, but I'm trying to help the intuition here, yes.
In this case, isn't VM random, actually? Because the second finisher is also...
Yeah, VM's random. That's what's kind of remarkable here. So this statement is conditional on VM. All this is conditional on the selection. And then it's uniform. So but then having condition, you can do it marginally. So it's true conditionally. Everything here is random. Eta is also random, right? Because it's the variable you chose. I mean, you're going to want to infer about the variable that appears that you chose. So all these things are random, but conditional on the selected set. They're fixed. This is uniform, and then it can uncondition. So I've spent many hours looking at this result, and it's John's. It's very subtle, but I think it's quite remarkable, and its applications are clear. Well, its applications. I mean, this is what we used. This is exactly what's used to produce this picture, right? I use that. We basically apply the polyhedral lemma with the A and the B given by the Lasso. I mean, whatever the Lasso's active set was, and then we invert that probability statement to get the selection intervals. And similarly here, the A and the B came from forward stepwise regression. So every procedure has its own selection, and that selection tells us how to judge it. We need to know the selection to judge fairly what it's done. Yes?
The intervals that you're constructing are then marginal intervals for each variable, so can you make them jointly?
That's a good question. So these are marginal. To make them joint, we have to basically do a Bonferroni adjustment. So these are, each one is individual. But we're working on well, one thing we have, which I guess I mentioned in the list of papers, we have a way of actually, with other students, we have a rule which you can apply to these p-values, a sequential p-value rule which achieves BH control. So there's a rule which you can apply to these p-values, which if you stop at the prescribed place will have control false discovery rate. So that's one way to kind of use them together. But if you're interested actually in confidence limits, these are just marginal.
Does this account for the correlations among axes?
Does what account for them?
Correlations, or if some axes are sort of collinear in a way.
When you say this, you mean this whole theory?
The method, yeah.
Yes.
Is it just marginal? Or?
No, of course, no, but I mean the construction, I mean X is all over the place here, yes, but the result is just the marginal, yes.
But it does depend on the Gaussianity.
Yes.
As you get more guys involved,
Yes.
it becomes...
Yeah. So it depends on the Gaussianity. Empirically, it doesn't seem to depend much on Gaussianity. Though when we apply it in other settings like principal components, which I've got another student working, then it's very dependent on Gaussianity. Somehow regression is forgiving because it's got sort of a central limit theorem happening, but other applications maybe not so. Is there another question?
So when you use that pivot, you're doing inference conditional on the selected model.
Mm-hmm.
So it's not taking into account the additional variation from model selection.
It's not taking account, say again?
The additional variation that came from model selection.
Oh, it is. It is. That's the whole. So that's the whole selling point of this, I guess, right? So, I mean, these p-values, they adjust for the fact. So, this guy's this p-value tested all hypothesis that the next guy entered is 0, given the selection that occurred before it. So it's using the identity and the signs of the variables that were entered first. So it's explicitly accounting for that selection. And the fact you can do it in a formula, I think, is pretty remarkable. I mean, again, I'm giving John Taylor the credit where credit is due. I mean, you could try to do these kind of things with permutations and things and bootstraps, but it doesn't really quite work out. This with a formula actually gives you exact adjustment for selection. Yes. Did you want to ask again?
I mean, if I'm conditioning on the model that I selected,
Yes.
I won't be getting the variation that I would be getting. For instance, if I bootstrap the whole way from the start and selected a different model, they precisely condition on not happening.
But we should talk later, maybe. There's a lot to your question. Yeah. You have another question?
So technically, you could use this lemma to, probably you've done this already, to look at confidence bounds for stuff like matching pursuits and orthogonal matching pursuits. These greedy algorithms for selecting.
Well, of course, matching pursuit is sort of like Lasso. So if it's polyhedral, the answer is yes, easily. Whoops. But if it's it's not polyhedral, you can resort to MCMC, right? So even if this selection is not so simply, then you can resort to that. But yes, in principle, yes. The back.
Will
When you use Lasso, typically you use cross-validation to choose a lambda. So in this case, you conditioning on the fixed lambda, you're taking into consideration lambda is also cross-validation.
You must be a Stanford graduate, are you? That's a very good question. No, that's a good point. Sorry. That's a very good question. So yeah, I pushed that under the rug. This is all for fixed lambda. We have a version of this for Lars, which applies to each step of the Lasso sequence. But if you want to use fixed lambda and you choose a lambda by cross-validation, this is not actually giving you the right coverage. We're working on, I think it's a small effect because it's kind of orthogonal to the inference, but this is strictly speaking for fixed lambda, not chosen by cross-validation. But I think one can get there. So I should, well, that's fine. I don't have a huge lot more to say. So if you want to trial this, in about 3 weeks, there'll be an R package on CRAN, which does all of this for forward stepwise, the Lasso for Lars, and you can even things like if you decide to stop at AIC, you can wrap that into the selection rule and get exact inferences given the selection by AIC, the stop by AIC. So this is all coming soon, and this will be an ongoing project. We'll pull in some of the other cases, which I'll just on one slide say there's a lot of activity at Stanford and other places now applying this to lots of different situations, like as I mentioned, principal components, bootstrapping, many means, lots of things. John especially has gone hog wild with this stuff. He's very excited and doing a lot of applications of this and new theory. So it's all very exciting. And I mentioned this paper is actually impressed. This is the one that takes those p-values and turns them into a stop. You can drive a stopping rule, sequential stopping rule. It gives you exact FDR control. Okay. So, I don't know how I'm doing with time, but I'm going to just wrap up just 3 points. My first sort of general appeal was it's essential to work, to me at least, to work with real scientists. It helps, hopefully, the scientists, but also helps you in ways which are unexpected. I've talked about sparsity, which I think is a powerful framework for small and big problems, right? The last set of problems, I didn't mention that everything I said in the last section works for p bigger than n, but you might care more about it when p is less than n, where you want to understand your model as opposed to use it for prediction. As I mentioned, there'll be software available and hopefully lots more development in this post-selection inference field. So happy to take more questions. Thank you. I guess.
In the interest of time, maybe we can have one question now because there were a lot, and then take the rest of the questions.
So the one question goes to your first point there. Does this mean statisticians are not real scientists?
Touche. I think we are, yes. With real scientists.
So you might want to rephrase that.
That's good. Do we want a real question still? Okay.
I said this, I've talked to you about this before, but I think it might be, I felt like when people were interrupting and asking questions, there's one little point of confusion that would be helpful to get your take on, and maybe it would help if you even presented, if I'm understanding it right, if you make this point during the presentation in the future. My understanding is you start with a problem that is in principle insoluble, which is to say we have more variable data points, and we want to get the right model, and we want to do inference about it. Mm-hmm. We can't solve that problem. We'll never solve it. But what we can do is we can change the problem a little bit. We can do something clever. We can simplify. We can make some assumptions, and then we can make some progress. And what I understand you to have done is to say, well, you can take a procedure, and you can say, here's the operating characteristics of this procedure. Mm-hmm. And that's really useful.
Yep.
And I like it very much, but it's not solving the big impossible problem.
Right. There's no claim here that we're finding the right model. We're doing inference for the selective model. Right. Whether that's the right model is a whole other question, which people like Peter will solve for us. No? Maybe not.
There is no right model.
Okay.
Okay. Thank you.